Swayam Prabha. Digital India. Educated India.
All right, welcome everybody. I did tell you that I'll work some problems on these cyclohexanes. Let's do it. Here are some naming problems and here are some conformer problems. Let's look at the naming ones. Let's say you're given a Newman projection and asked to write the name. I mean, how do you go about doing that? Do you start kind of taking these apart, or what do you do? Well, one of the easiest things to do, or at least the easier thing to do, would be to look at it from the top and draw it like a flat cyclohexane. So you know that these groups are above the plane and these are below the plane. So that's something to remember when you're drawing this. And then where do you start? Well, you can start anywhere, but since this one is on top, you can put that as your start place. Then when you look down from there, this is the circle is the next carbon. That's your circle carbon. On that circle carbon, above the plane is going to be a T-butyl group. Below the plane on that circle is a hydrogen, because you're drawing it flat, because you're looking at it from the top. So it's not going to look like a chair anymore. It's not going to look like this anymore. So it's like in your face look. Then when you're looking at it like this, the circle and the dot are actually two carbons. You're looking at it like this. The circle and the dot are two carbons. When you look at it, you'll see the bond. So here's the circle, here's the dot, and here's the bond. So that's the bond there to the dot. On the dot, the hydrogen is above and the methyl is below. So hydrogen is above and methyl is below. Then you go into the next CH2 here, which then is connected to this side. Again, same thing. When you look at it from the top, you see the bond. So dot and circle is just nothing but a line there. On the dot here, you're going to see a isopropyl that's on top, a hydrogen below the plane. Then you go into the circle, and that's your circle. And the circle carbon, you're going to have a CH2 connecting to that, the first dot that you saw. Methyl is above the plane, that means you put it on a wedge, and hydrogen is below the plane on the circle. So that every one of these has three things attached to it. Isopropyl hydrogen CH2, and over here methyl hydrogen CH2. So the methyl is up, hydrogen is down, and then the CH2 is to the right. Now that we've written it out like this, then we can write a name for this. So what would be the name of this molecule? Let's look at it. So where do you even start numbering something like this? Well, the rules for naming cyclocompounds is that you give the first lowest number by alphabetic priority. Then you try to go around the ring in whichever direction that gives you the lowest numbers for the other groups. So here, T-butyl is going to be B. So that's number 1. Then we can go over here and let's see, this is 2, 3. So if I go around this way, these are both methyls. So this will be 3, 4, 6. Whereas if I go this way, it's going to be 2, 4, 5. So 2, 4, 5, and you know, even if you add them up, it's going to be less than 3, 4, 6. So we would go this way instead. So let's go down and number it this way. 1, 2, 3, 4, 5. Then we just arrange them in alphabetic priority, and T-butyl is going to be mentioned first. 1 T-butyl or T-butyl, or 1/3 butyl, whichever you prefer. B, and 2 and 5 have methyls. 4 has isopropyl, so we have to mention that first. 4 isopropyl, and then 2, 5 dimethyl, and the parent is going to be the nice beautiful ring here, cyclohexane. let's just do another one. And sometimes they may even put stuff on these CH2s here. So therefore, because it's substituted like this, they're just drawing one Newman projection for both. So if you see something like this, well, then what do? Same thing all over again. I'm just doing this just to show you that that's a possibility sometimes. So here you're going to have a look from the top. Again, instead of looking at the chair on the side, you're looking head on. So we're going to start here. So that's that. And then you're going to do the circle. And you see the circle connected to the dot in front. This dot is that. Then it's connected to this. And over here to this. And to the circle at the back. And that's connecting to this. So it's the same thing. Remember, this is 1, 2, 3, 4, 5, 6. So on 2 carbon, carbon 2, you have a group that's going above the plane. That's an ethyl. You have a group going below the plane. Now that you're drawing it flat, you got to put wedges and dashes. Otherwise, you won't know where they are. But here, we don't really need to do that because it's pretty obvious. These are above and these are below. This one you do. Now, on the dot, isopropyl is above and hydrogen is below. This is already spelled out for you. There's no guesswork there. You just write it just as it is. Then on number 5, chloro is up and hydrogen is below. And over here, ooh, you got a big guy kind of falling down there. And so methyl is up and sec-butyl is below. So now we can just go ahead and write the name for this looking. So this is just an eye, guys. I know my eyes don't look too great, but that's what it is. So where do we even start numbering? Okay, so ethyl, isopropyl. I'm just going to do like the simple common naming. You can also do the complex one if you want to. Ethyl, chloro, sec-butyl. All right, so sec-butyl starts with a B. So let's see, sec-butyl is B, this is ethyl, E, then this is isopropyl, I, then here's an ethyl, and here we have methyls. I'm just going to put M for those, and we have a chloro. Chloro groups are not like, hydroxyls or something. They don't have any higher priority than alkyl, so you just treat them just like you treat an ethyl or a methyl when you're doing alphabetizing. So B, and then C, then E, then I, and then M, pretty much. So 1, and then let's see, 2 chloro, this is ethyl, so, and then the numbering 2, 3, 4, 5, 3, 4, 5, 6, so this is also better for numbering. So then that's going to be 1 sec-butyl, or you can just put sec-butyl. Writing 1 is optional, although a lot of the programs, if you're doing online homework, they would require to write the 1. I'm just writing this like this just to show you that that is optional. You can write 1 sec-butyl or S-butyl or sec-butyl. They're all going to be fine. Those are the 3 ways in which you can write the name of that group. So 1 sec-butyl, and then chloro is next, 2 chloro, and then ethyl's next, 3, 5 diethyl, and isopropyl would be the next, 4 isopropyl, and then that's going to be 1, 3 dimethyl. And did I leave anybody out? I got everybody in there, so that's cyclohexane. Here's something, I just put this in because we didn't have time or maybe even space to go over this. What if it's a straight, this is not a cyclohexane, as you can see, I only have one of these circles. And what if I were to name something like this? What would you do? How would you write it down? Straight chain. So again, it's a straight chain. They're just doing a Newman projection through one of these. And how do you then go about it? Well, same thing. Look at it from above and you'll see that bond. So look at it from above, see the bond, and then just write it out like this. So here's your circle. That's your circle carbon. That's connected to the dot in the front. That's your dot and that's your circle. Now you can just put the other groups. Again, remember, if they're coming up, it's a wedge. If they're going down, it's a dash. So on the dot, you have a methyl coming up, an ethyl going down, and then you have this chloro. Ethyl coming down, and then you have this carbon that's connected to a chloro. Now over here, they're not specifying the stereochemistry of the chloro. So if they did, let's say, put a wedge, well, that would get into more like a stereochemical naming. We're not there yet. So you can see that's connected to a carbon, and that carbon's connected to a chlorine, and then there are two carbons on there. What's connected then on the other side of this circle? The circle then, if you look at it, the circle, it's connected to two things, actually three things, a T-butyl, isopropyl, and a hydrogen. So let's draw them in, T-butyl, isopropyl, all around that circle, and a hydrogen. Now, we haven't learned stereochemistry yet, but if you did, then you would put these as wedges and this as a dash, and do some 3D diagrams, but we are just doing a naming without stereo naming because we haven't really covered RNS and so on, all of the other stuff that you'll learn later. Now we've written our molecule down. Now let's try to name it. How are you going to name this, and where do you even start? Do you start somewhere here, go all the way here, left to right, right to left? So many possibilities. So just to review the rules. The rules say you got to find the longest chain and then start numbering from the end that has a substituent closest, and then try to give the other substituents the lowest numbers possible, right? So where do we even start? If I start here, 1, 2, 3 before I hit a substituent. If I start here, 1, 2 before I hit a substituent. So obviously this is better than this. But is there any other possibility? Let's say 1, 2, 3 for this junction, 1, 2, 3 for this junction. So this is the same length as this. When you go over here, this is only 2 and this is 3. So you go up. So that's pretty obvious. Over here, these are the same number. However, you're going to meet 2 methyl groups right as you start on the second carbon. Whereas here, you'll only meet 1 methyl. So this is really not a good way to start. Here you have more substituents earlier on, right there. When you're wide awake, you want to hit all those scenic spots. You don't want to do them like when you're almost going to bed. So 3, 4, 5, 6, 7. So then on 3, we have an isopropyl. 4, we have an ethyl and a methyl. And on 5, we have a chloro. So what looked like a T-butyl now is actually part of the chain. So that's why it helps to write it down like this before you start naming on here. So then we can alphabetize them. 5, well, chloro would come first. 5 chloro. And then here's an ethyl and an isopropyl. So ethyl before isopropyl, 4 ethyl. And then 3 isopropyl, and then we're going to have 2 to 4 trimethyl, and the whole thing is 7 carbons long, and so that is going to be a heptane. So here's how to name molecules that are drawn as numens. All right. So let's do some practice here. Draw the most stable conformer, and maybe we can even try to name them. So over here, let's see, we'll start with this one. First, find out which one is the biggest group. If they're asking for the most stable, you need to put the biggest group on the equatorial position. So here, we want to put this equatorial because that is the one that is going to be the biggest and the bulkiest. So you don't want 1,3 diaxial from that. So you want to put it away on a side. So let's draw the chair here. This is an oxygen in the ring. The easiest thing is to start drawing your ring, put the oxygen there. Then you do everything else the same. It's just there's an oxygen in the ring. That's the only difference. Now, this is going to be, well, this is, if you number, this is typically the way you number this molecule. And I'm sure a lot of you might recognize this as glucose. This is the one that pretty much is 2/3 of your food. The wood has all glucose polymer, which is cellulose. So you build a house out of glucose units that are linked. You eat food, that's glucose units that's linked and starch. And you're wearing clothes that are cotton, which is basically glucose units that are linked, okay, to make starch, cotton, a big part of your life. So let's look at this. 1, 2, 3, 4, 5. On 5, you want to have your group going equatorial. So the one that you have drawn now is all axial. So this is 2 is going down. So glucose is never ever going to do this. But since I've drawn that chair, and then 5 is going to be up. Okay, so you'll never catch glucose looking like this. Okay. It's going to immediately flip to the other chair that's going to have the oxygen over there, and same chair, except you got an oxygen in the ring, a peronose ring. And then again, you're going to put all of these above. What's above will be above, and what's below will be below. So this is above the plane, which is an OH. This is below the plane, which is an equatorial. Number 3 is OH above the plane. Number 4 below the plane. And number 5 above the plane. So this is a CH2 OH. So you can see that there is absolutely no doubt this all equatorial is the most favored molecule in nature, because you see so much of it. Let's look at this molecule. So over here, let's look at this molecule, try to draw a chair and see which chair is going to be the best. Again, do the same thing. Again, I mean, if you don't know where to start, start with that. Those are the 2 parallel lines. So just draw them out first. And then you can put this as 1. This is going to be your peak that's going to go up. So you put your dot and you connect the dots. Now, up, up, up. That doesn't mean they're all axial. It just means they're above the plane. So let's say this is your chlorine, this is this. Up is equatorial. 2 has nothing, 3 has isopropyl, and that's going to be equatorial. That's an ethyl there. And over here, 4, 5, 6. This T-butyl guy is going to be pointing to the sky, and you know that is really, really bad. That's very high energy. So this molecule here, it may look like, oh, you are 2 equatorial and only 1 axial, but look at the numbers. The axial here is 22.8 kilojoules per mole, and these really aren't contributing that much. I mean, the Gauss interaction here between that and that, probably not that much. So, you know, this is kind of really high in energies. This is the one that's really going to be causing all that strain, unhappiness, and misery in this molecule. So it just flips over to the other side, and we'll see the energy there isn't going to be that much. So over here, when you flip this up and go over here, your chlorine is above, so it's going to be above. Your ethyl is going to be above, so that's going to be above. And your 4, 5, 6, this carbon is going to be all on the side. It's almost like you put the monster away. These guys are not too bad, 2.0, and ethyl is 8.0. So total, this is 22.8, and this is about 10.0 kilojoules per mole. And that 12.8 kilojoules per mole difference is going to make this almost like a 99%. So whenever you see T-butyls, you really have to get them out of the way and put them equatorial. So this is going to be where it is. All right, let's just do one more for fun. Again, just to kind of reiterate this concept. Here you got a ton of stuff going on. What do? Again, think of it as looking from above. Looking from above. And then draw the chair. Make these 2 lines the parallel lines. Put these 2 parallel lines. And this dot is going to be this dot. And this is going to be on the top. So you're going to draw this out here. When you're looking from above, whatever's on the wedge is going to be coming above the plane. So here's your eye. Whenever you see above, wedge is above the plane. Above the plane can be axial here or equatorial here. So we don't know that unless you draw this. So here on this dot, T-butyl is above the plane, which is axial. Chlorine on 2 is on the second carbon is above the plane, which is also axial, This is equatorial, this is axial. This is the next carbon above the plane, ethyl. And nothing here on this carbon. You have an isopropyl again above the plane. So even though they're all on wedges, you can see some of them are axial, some of them are equatorial, which is why you can't really guess from this. You have to draw this out. There's no rule that wedge is axial or dash is equatorial. That's totally wrong. Wedge can be axial or equatorial, depending on which position it is. And the way you draw your chair determines that. Now you're going to flip it. So these 2 parallel lines, then we draw them like this. And do the same thing again. All right. Let's look at where we're going to put this. I just changed the colors here, so it's going to be a little more obvious. So we're flipping this up. Up is up on a pointy up is always axial. Here, this is carbon number 2, that's going to be above, and here it's going to be equatorial. Next carbon above, this is on a pointy, this is going to be over here. So above is going to be above pointing up, the ethyl. Oh, we do have one more, which is going to, there's nothing here, and here this is above pointing up. Oh, this is going to be really nice, even though the chlorine's axial, that's only 2.0 kilojoules per mole, whereas these guys are all pretty much standing up here lots of 1,3-diaxial. It's going to go back over here. This is your most stable. This is unstable. That's a pretty obvious case. Sometimes you have to evaluate using energies. If more groups are in one of the conformations, then they are like a lot of equatorial and a few axial, then you have to evaluate it. But when you have a lot of axial, it's like a very straightforward case. All right, let's look at this. Decalene. What's decalene? Decalene means you have 10 carbons. And it's just a common name. And where are the 10 carbons? They're in 2 cyclohexane. So you have a cyclohexane joined to another one. If you're going to really name it as a bicyclo, you could say 4,4,1 bicyclodecane, right? We're just calling it decalene. We're just drawing this, and we want to know which is better. Cis-decalene, where you have, let's say, both of these on the same side, or trans-decalene. Which one do you think is going to be more stable? Is it going to be obvious from this or not? So this is your cis, this is your trans. Let's draw them out. Let's draw each of these out. Let's draw this out first. So here is your cyclohexane. Let's do the same thing we did before. Dot, dot, and connect. And here's one ring. So you have one hydrogen up, one hydrogen down, which means you got to have the other ring coming out like this. So let's draw this part of your chair over here. Again, so you have put your parallel lines like that, and this is the dot here, and you connect the dots here. So that's your trans-decalene. Let's draw the cis-decalene out and see which one's better. So you draw one of the rings, just like here. So you draw this out like that. Now your hydrogens are going to be on the same side, axial and equatorial here, which means your carbons are going to be on the same side. Your carbons are going to be different. So you have to have your carbon going like this here, and over here you're going to go like this, equatorial. Then you draw your parallel lines, and there you go. Connect them. So over here, you can see that this one is going to be almost like, on opposite sides, these groups. So the gauge interaction isn't that high. Here, you're going to have some gauge interaction between here and here, here and here. So therefore, this is going to be a little unhappy. These, you can see, are going to be on opposite sides. So there's an anti. So this is unstable. And this is stable. Now these chairs can flip here and flip here, but they can't go from here to here. Okay, for that you have to literally break this bond and fix it in a different place, right? So these are 2 different molecules, 2 different stereoisomers. You can't flip from here to here. You can flip this chair and this chair, but it won't go over here, right? The stereochemistry here is different. All right, cis and trans. This is just some examples for you, and hope this helps. And don't hesitate to let me know if you have any questions. Talk to you soon. Bye.